Testing, testing, 1, 2, 3, testing, testing. Good morning! I just, clear the chalkboard, jeez. Get out of here, you. Blech. There we go. Sorry for my tardiness. What? No, it's not tardiness. I'm on time. Ha! So, let's see here. 24 to 21. Okay. I think I saw I had 2 likes, and like the stream hadn't even gone live. That's pretty impressive. Thank you for the likes. Everybody subsnurb. Subsnurb to the channel. The channel needs your support in order to be alive. So subsnurb to channel, please. I'm just kidding. You don't actually have to subsnurb. So, let's see here. Ah, yes. Okay, good. So, some of you have got the memo then. For those of you who have not yet found the online stream, I hope that you will shortly. Ooh, how many people actually went to the room? Are you in Hamilton Hall right now? If anybody's there, I'll give you the projector code so you can put me up on the big screen. So yeah, so in terms of announcements, there is a fairly lengthy announcement about the setting up of getting everything running. Pre-tutorial setup important, which was posted last Monday. If you haven't already done that, please do so. And, you know, if you're having trouble getting onto GitLab, there's a link posted in the announcements, which should be of some assistance as well. Ah! 18% of people are actually in the room. Okay. I'm going to give you the magic code. Boom. There you go. Do with that what you will, but you didn't hear it from me. Ha! So. Good. I'm going to sneeze. Excuse me. Pardon me. So. So, last week, I had to actually, not do my, my lecture on Wednesday because my wife was sick with the flu, and then I got the flu on Saturday, and I'm still, recovering a little bit, so, I don't want you guys getting what I got, so there we go. But, I'm, you know, I'm probably going to be fine by tomorrow. I think I just need the one day. I think actually, like yesterday I developed a cough, and I think it was, not even so much the flu itself that caused the cough, but I think it's, like the acid burn from all of the upchuck that was, splashing the back of my throat for a almost 12-hour period at intervals. Somehow I got a... somehow I even got a better night's sleep than my mother did. My mother? What? What am I talking about? My wife? What? Uh-oh. What am I? My brain is still scrambled from it. Felix's mother. My child's mother. That's what I meant to say. She's going to be a mother soon. Anyway. Oh. I see some what will we be doing during the tutorial tomorrow? A lot of us are still having difficulties getting everything set up. So if you're still having difficulties getting set up, then that is what you're doing in your tutorial tomorrow. Get your TA to get that set up. Otherwise, there's like, some degree of like programming activities which have been provided. So we need to keep moving on the lecture material though, because we're behind on it, and we need to make some progress. So good. So let's roll. So last time we got as far as input and output, reading to and writing from and writing to, standard input and standard output. So let's talk about data types, because we should know what data types we're using before we get much further. So in C, as opposed to other languages, C is very, very particular about the bit size or the number of bytes composed by each variable, by each element of an array. This is because C needs that information to be able to perform array offset calculations and general memory management stuff, which most languages just kind of hide from you. So here are your fundamental data types. The unaltered data types are integer, floating, float, double, char. Double is double precision floating point number. So floats by default are only 4 bytes, so you'll be wanting to use doubles most of the time. And then you'll notice like a whole bunch of these things which have modifier words on them. So let's take integer for an example. We have a difference between signed and unsigned integers. Unsigned integers, they can't hold negative values. They're only positive. Signed integers can be negative or positive. And then you have short ints, long ints, and long ints. This is a distinction that's drawn for somewhat historical reasons, but essentially, you can use only 2 bytes to represent a short int if you an integer if you want to, by declaring it as a short integer. This is mostly for like memory efficiency and memory management stuff. Not using more bytes than you need for the particular number that you're storing. Like if you have a variable that ranges between 0 and 12, you don't need to allocate 8 bytes for it, right? You only need to allocate 2 bytes for it. But so it goes. Each one of these data types has a corresponding format specifying placeholder used thusly. So use the one that's appropriate to the data type that you're printing at all times. Thank you. So, good. If you're not aware of what a floating point number is, those are numbers with a fractional component, so numbers with decimal places. Good. You may have noticed that the foregoing slide didn't have Booleans on it. Boolean support was added to C in ISO/IEC 9899:1991, which came out in, of course, 1991. It's the C99 standard. Unlike most other languages, Booleans are not part of the C prelude. In order to use them, you have to include the standard Boolean library. So, to use Boolean data types, you must include this line. So that may, that may shock and appall you, because obviously the concept of a Boolean is older than 1999, So what did C programmers do for Booleans prior to the existence of the dedicated Boolean library? Well, generally, C programmers would use integers to represent Booleans. 0 was defined as false, and all other values were defined as true, though 1 was typical. It turns out that this is also how the standard Boolean library does things. It basically just encoded the stylistic manner that had been adopted by C programmers and codified it. But you'll find that if you perform Boolean arithmetic and, Boolean operations, if you have an integer with 0 for representing false and 1 representing true, then all of these operations still work out the same way they would otherwise. So it all worked out, but it's just kind of an interesting little historical note. So that's why you have to import Booleans in order to use them. So more memory concepts. You should know what a variable is by this, if you've done Python, you should know what a variable is, but let's go over it anyway. Variables are units of memory that have been assigned an identifier. The amount of memory allocated is dependent on the data type the variable is declared with. The specific arrangements of ones and zeros at that memory's location, at the memory location the variable indicates, is the value of that variable. So it's very, very, very important concept. This is like pre-pointers, right? You must begin to distinguish in your brain the difference between the value stored by the variable and the location the variable is stored, right? The memory address of the variable versus the value stored at that memory address. That is an important conceptual distinction. Variables may be read from without disturbing the underlying memory. When a new value is assigned to a variable, the pre-existing memory value is overwritten with the new value. In general, things work pretty much the same way as they do in any file system. In Python, variables don't need to be declared with a data type. That's because it uses dynamic typing. It uses parametric polymorphism, if you want to get technical. The Python interpreter manages the memory representation of variables. Python does this interesting thing where, like, if you have a counter, right? Let's say this counter is run for a very long time, and it exceeds the storage capacity of an integer, right? The sort of base integer type as it exists in C. Python will slap more memory on that variable continuously so long as you continue adding to it. So the size of the integer itself grows dynamically as the program is running. This is not what happens in C. In C, if you exceed the storage size of an integer, you get something called wraparound. So basically, and I can do this like, I'll just quickly explain the concept of wraparound. Let's say we had a 4-bit integer, right? Or let's leave it like that. What happens when we add 1 to this, right? So this is equal to 8 plus 4, 12. So to add 1, we do that. To add 1 here, so if we, get out of here, you. If we add 1, then that gets, you add 1 and 1, that gets 1 with 0. That's like a carry, right? Plus 1 is 1, 1, 1, 1. So the question here, this is just distracting. So the question is, what happens if we add 1 here? Well, what we actually get is we get a 0 here, carry the 1, right? 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. So that would be the result. However, because this is C, these integers are of fixed size. So anything that falls outside of it is deleted. So, if you have the maximum number of bits in a number, and you add 1 to that, it wraps around and becomes 0. So there you go. I think I was wrong. I think it's, is it 12? Messing up my binary now. It's like, well, the values of these bits are 8, 4, 2, and 1, right? So this one will be 50. This is 15, right? Because it's 1, 3, 7, 15, right? So this one is 14. This is how binary works, folks. You'll get used to this. Yeah, so I was right. It is 12. And then that one is 0. Each one of these bits represents a power of 2. In order to get to the number, you add all of the powers of 2 corresponding to the ones, right? So 8 plus 4 is 12, right? 8 plus 4 plus 1 is 13. 8 plus 4 plus 2 is 14, etc. Right? So that's what wraparound is. All right? This happens in C, but this is like one of those nasty little surprises that they try to avoid in higher level languages, right? So, you should know that that happens. In C, the type declaration tells the memory system how much memory to reserve for the variable, so the information must be present. Incidentally, most variable, like a regular integer in C is 32 bits, not 4 bits. I'm using 4 bits here for the purposes of demonstration. So, yes. So we need to know how much memory to reserve for a variable, so this information must be present upon declaration. In Python, they just kind of like, we'll figure it out later. We'll allocate you more than you need, and then just chop it down if we need to, and that's much less efficient. C is much more efficient, because you have to know ahead of time. So C uses what's called static typing. The typing must be known before the thing gets executed. Variables in the same program will not necessarily be allocated in adjacent memory cells. That'll be more interesting when we get to pointers. So, let's talk about basic operators. These guys you should already know. This guy you should already know. All of these guys you should already know. Arithmetic operators are assumed knowledge. These guys, however, probably the first time you're seeing them. You've got increment, decrement, prefix, and postfix operators. The increment and decrement operators, plus plus and minus minus respectively, either add or subtract 1 from the operand. So x plus plus means x plus equals 1. Whether the operator is prefix or postfix affects the semantics. So if the operator is prefix, that is, it's plus plus x, the increment is executed before the containing expression. So this is increment this before we execute this statement. Postfix means increment it after. Yes. Because, okay, this is, I'm disturbed by how late late these replies came in, so I'd like to just do a latency test right now. I'm going to clap my hands, and when you guys hear the clap, I want you to just type something into the chat, or put a smiley face emoji or something to indicate that you received the transmission, and I'll see how long the latency is, okay? All right. 3, 2, 1, clap. Ah, actually that's 7 or 8 seconds, which is like, okay. That's actually better than usual. Usually it's around 12 seconds. Okay. Boom. Excellent. cool. So, anyway. Because of this implicit assignment, using plus plus or minus minus on an integer literal is a syntax error, because you can't assign to a literal, right? So, here's an example. Let's say we have variable 1 and variable 2, both given a value of 5, right? Let's say we display variable 1 is equal to, and then var1 plus plus, and then variable 2 is equal to, and then it's plus plus var2, right? The first one will print variable 1 is equal to 5. The second one will print variable 2 is equal to 6. However, if you had like an if statement down here that said, if var1 equal to var2, then print these are the same, then it would print that as well, right? By the time we hit this return statement, both variable 1 and variable 2 will both have the value 6. Both times the increment will be performed. The question is it being performed before or after the print statement? In this case, it's being performed after the print statement. In this case, it's being performed before the print statement. And incidentally, putting one of these on its own line with a semicolon, perfectly valid statement. In fact, you'll see that a lot when we do loops. It's like, at the end of the loop, instead of I plus equals 1, it'll just be I plus plus. It's like saves one character. So, bitwise operators. We will get into bitwise later on in the course, but these are operations that occur according to the bit values of the integers themselves. So, for example, oh, the not didn't come through. So, we've got 1's complement, which just inverts the bits. We've got left shift and right shift. And we've got and, or, and XOR. So, if we have X and Y here, right, with 1's and 0's, the symbol didn't come through, but this is 1's complement. 1's complement of X simply inverts every bit in X. If we take X and we left shift it by 2, this takes the value of X, and basically these guys are taken from here, right? It's just been shifted left by 2, and then 0's are put in place of the opened spots. Right shift is the same. You basically take the whole number, shift it down by 2, and then backfill with 0's, right? Left shift and right shift are actually, technically speaking, the same thing as multiplication and division by powers of 2, because this is binary arithmetic, of course, and they're slightly more efficient than actually calculating powers, and by slightly I mean a hell of a lot more efficient than calculating powers. So this is a neat little time saver for you if you're ever multiplying or dividing by powers of 2. So and then. Bitwise AND operates pretty much the same way as a Boolean AND operation. So X and Y, if you take 1's as true and 0's as false, we should all know that 1, like, true and true is true, true and false is false, false and true is false, and false and false is false. That's how bitwise AND works. Bitwise OR works in the same way, but on the principle of if either of these guys is 1, then this guy's 1, and only if both are 0 is this guy 0. Exclusive OR is kind of interesting. It's only 1 if the inputs are different. So if it's 1 and 1, that actually goes to 0. And if it's 1 and 0 or 0 and 1, then you get 1. So there's a rough summary of bitwise operations. We're going to have a point later in the course where we talk about them in more detail. So, now let's talk about relational operators. I know this is like throwing operators at you, but yeah. You need to, like, you should already know most of these, so. So, in C, equality comparison is two equal signs. This is the same as Python. Inequality is exclamation point equal sign. So this is x is not equal to y. In Python, they may have taught you to use the not keyword. The not keyword does not exist in C. You use the exclamation point instead. It's a prefix operator. You've got greater than equal to, less than equal to, which should be the same as Python. However, in Python, you have not, and, or. These are the symbols for those respectively. So not is, again, prepended exclamation point, and is two ampersands, or is two vertical bar characters located above your enter key. You'll notice that the Boolean AND operation is the symbol for Bitwise AND written twice, and the same is true for OR and Bitwise OR. That helps you remember which ones they are. Any questions so far? Good. So, in addition, so to speak, we have a large variety of assignment plus operation operators. So, you've probably seen plus equals and minus equals previously. But perhaps you've never seen modulo equals or left or right shift equals. All of these operators are valid operators in C, which combine regular assignment with the operation specified. Simple. So, let's talk about keywords. Generally speaking, you can see how big a language is by the number of keywords. What's the difference between logical operators and bitwise operators? Logical operators operate on Boolean values. Bitwise operators operate on any value, but integers are, most common. These guys normally hang out inside of conditional statements, like in if statements and loops. These guys will often have more exotic uses. You'll see them, like, when you take 2TA4, for example. To sort of, when you need an operation that addresses like one particular bit inside of a number, these are the operators you want. These guys are just like, the way that you remember using and or and not from Python programming. So, good. So these are all of the keywords that exist inside of the C language. You're not allowed to name any variables after keywords. It is wrong and bad, and you should be sorry when you do so. But this is what you have. You have auto, break, case, char, const, continue, default, do, doubled, else, enum, xturn, float, for, goto, if, int, long, register, return, short, signed, size of, static, struct, switch, typedef, union, unsigned, void, volatile, and while. And you will know what almost all of those keywords mean and do by the end of this course. Additional keywords added by C99, bool, complex, imaginary, inline, and restrict. And then in C11, align as, align of, atomic, generic, no return, static assert, and thread local. We're not going to talk about any of those, really. So let's talk about if statements. If statements are written a bit differently in C, but are otherwise identical in terms of functionality. So this is a regular if-else statement. We've seen a couple of these so far. If condition statements, else statements. One thing to note, the elif in Python is replaced with else if with a space. Wow. I don't know how far away you are, but if you're like responding to that clap, that was like 10 minutes ago, man. That is hella latency. Holy smoke. So, elif will cause a syntax error, so if you get that, just expand that out to else if, please. So, Mommy, can we get an if statement? No, we have an if statement at home. The if statement at home. That's just a little joke. If this doesn't make you cringe, you're not a real programmer yet. So. Python technically has added its switch cases back in at this point, but they do like pattern matching in like functional programming style, which is like, you know, not exactly what a switch case actually is. So let's talk about switch cases, because, you know, some of the examples that we're going to do have switch cases, so you need to know what they are and how they work. So, a switch case performs essentially a rough equivalent of the functionality of a series of elifs that are all testing one variable. So in this case, switch x, right? So x is the variable that we're switching on. Case 1 executes if x is equal to 1. Case 2 executes if x is equal to 2. Case 3 executes if x is equal to 3. And default executes if x is not equal to any of those. It's like the else case, right? Not necessary. You don't need it. Cases, in order to terminate a case, you have to end it with a break statement. If you do not include a break statement, execution will pass through one case to the next. So, for example, case 2, right? There's no break statement here. So, everything inside case 3 will also execute if x is equal to 2. Make sense? Good. Well, let's take a look at we'll take a look at an example, but let's describe it first. In this example, x is the controlling expression. Incidentally, this doesn't have to just be a variable name. This could be a whole expression. The value of the controlling expression is compared to each case label, which is a literal of the return type of the controlling expression. Execution jumps to the corresponding case and exits the switch block when it hits a break statement. This means that execution may pass through multiple cases before exiting the switch block. Default functions like a terminating else in an if-else chain. If no case matches the value of the controlling expression, execution jumps to the default clause. So, this is what that looks like in terms of a flowchart. We evaluate our expression, compare it to case A, then if that's true, we execute case A's actions and then break and get out of there, and we do that for all of the cases listed, and then default if none of those are applicable. So, let's do a switch example. I've got this, I think, I should have this. Yeah, sarcasticgrades.c. We are going to take a look at a sarcastic program. When would you use a switch instead of an if? It saves you time writing. So, and you don't use elif in C, you use else if. So it saves you some writing, right? The alternative would be to go if grade equals a, else if grade equals B. Sorry, I'm still getting used to this keyboard. Etc. And you would not have the ability in an else if chain to have execution fall through one statement to the next easily. What you'd basically end up having to do is, say you had statement 1, statement 2. You'd have to copy statement 2 to up here, and as all programmers know, we try to avoid copying our own code to our own code as often as possible. So let's take a look at this example. So we're asking for a grade, which will be a character. We're scanning that character. C, by the way, scans a character, single character, and switching on that character. Case A, it's amazing, a smart person. Case B, you have met expectations. Note, no break. C, you need to study harder. D, at least you passed. F, well, they're always hiring in the army. And otherwise, that's not even a proper grade. So let's execute this thing. Enter your grade. A. So you'll notice, of course, that both these print statements are executed. And notice the lack of a new line character here. There we go. The lack of a new line character here means that they're printed on the same line. If we run this again, there we go. I didn't leave a space there. Perhaps I should have. And F, there you go. And say 7. That's not even a proper grade. There you go. See how this is working? Good. In some cases, it's not even a matter of, you need to know this because you need to use it yourself, right? It's entirely possible for you to, go through your entire programming career without ever having need for a switch case, right? It may just simply never come up for you. Or you can always, use other constructs. But other people might use switch cases. And if part of your job is to be expected to read and understand other people's code, then knowing how to use switch cases is a very good thing indeed. Why is it printing the statement below option A as well? I'm so glad you asked. Note the lack of a break statement. The lack of a break statement means that it prints this, then it continues and prints this, right? These should be thought of as labels, right? Sir, is that OBS? Well, yes, of course it's OBS. What else would I be using? If I insert a break statement here, right? Compile that up. GCC sarcasticgrades.c. Boom. Oh, what did I include? Something somewhere? Get out of here, you. There we go. There we go. If I just if I put a break statement in here, then I just get this print statement because this breaks out of the switch case. If I remove it, right? Recompile, execute, then I get both because execution goes, okay, I do this one, okay, then I do this one, okay, then I break, and then it breaks. Make sense? Hopefully. So, good. So much for branching. So let's talk about, go-to statements. So, a historical note on go-to statements. Go-to statements are terrible. If I ever catch you using them, then I'm going to flunk you instantly out of this course, using all of my powers vested in me by the university I will expel you straight from the university. No recourse, no trial, just immediate execution. So, historically speaking, at one point there was no such thing as an if statement, or a while loop, or any of these things. Program execution was controlled using goto statements. The reason I'm telling you all of this is when you do assembly later on in this course, you don't have if statements. You don't have while loops. All you have is gotos in assembly. A goto statement changes the value of the program pointer to some other spot in the code. So the code gets compiled to object code or machine code. That machine code gets loaded into memory as program memory, and the CPU maintains a register called the program pointer, which points to the currently executing statement, or this currently executing command, instruction is the best word, the currently executing instruction inside of program memory. A goto statement just grabs hold of the program pointer and manipulates it to some other portion of program memory. So, in BASIC, which is a very old language, this was done using line numbers. Lines had to be numbered manually. This generally made code just about impossible to read and originates the pejorative term spaghetti code. So the problem with using gotos for everything is it's almost impossible to suss out the actual line of execution of any program for any piece of code over a certain size and complexity. Basically, you have goto statements jumping in, jumping out, jumping up and down, going in and out, weaving through, and it becomes one great big tangled ball of string, and you can't tell where one line of execution starts and the other one finishes, and it's just a great big, it's like somebody drops a big mass of spaghetti on your plate and says, okay, I want you to modify this ball of spaghetti so that it fixes a bug. You know? It's like, what's the first thing you would do with the spaghetti? You would line it out, you would, straighten it out into its single lines of noodles. Right? So, this is what is meant by spaghetti code. Using gotos inevitably leads to spaghetti code. Therefore, don't use gotos unless you're programming in assembly and you have no choice. Technically speaking, if statements and while loops are syntactic sugar for specific goto structures. So, when the compiler finds an if statement, it translates it into gotos, because if statements don't exist at the CPU level. Only gotos exist. So they have to be translated, of course. Technically, modern control flow is less flexible, but it is much easier to use and reuse. So we did, when all of the big brains of computer science got together and they were like, okay, we're going to completely restrict things so that people can only use loops and conditionals. And we're going to use the force of culture to say that all gotos are terrible, because they are. And it's like, one person at the back's like, but technically speaking, you can do more with gotos than you can do with if statements and while loops, and then lightning hit him from the ceiling. Technically true, but not helpful. C has, in fact, goto statements, but their use is discouraged in the strongest possible terms. So, that being said, since the use of them is discouraged in the strongest possible terms, let's learn how to use them. Don't ever use them, but here's how you use them. To use goto statements, which you should never, ever, 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 ever do for any reason, you do the following. Number one, you create labels within your program. A label is any valid identifier followed by a colon. You then create goto statements referencing the labels. You can do really, really unrecommended stuff with this, like jump into functions. Jump into the middle of a function and then jump back out again. Really, not good stuff. That being said, you should be introduced to the concept for assembly purposes. So, speak not its name lest ye go mad. This program implements a do-while loop using goto. So, we have main. We set a label at the beginning of the loop. We then print a number, n, n++. If n is less than or equal to 10, we go to the label, right? So while n is less than or equal to 10, we are continuously jumping back to the beginning here, right? So that's a loop. As soon as that's not the case, we pass through that and return 0. So that is an example of a working goto. Again, do not ever use them. In C, there are 3 types of loops. In addition, we have 2 control statements for use in loops. If goto also replaces if, why do you use if in the code? No, you've got it backwards. If replaces goto. Goto doesn't replace if. The compiler has to take if statements and produce gotos for it in order for the program to execute on the CPU. But we, as programmers, never program in gotos, ever, for any reason. That's the whole point of me saying it's black magic. All right? Don't use gotos. If you use gotos, I'll find you. Okay? No gotos. Use if statements. But in this class, you need to know what the compiler is doing. So I'm telling you what the compiler is doing, right? And technically, you can use them in C programs. When you are creating a label, does it matter if there is tab or space before the characters, or does it consider the space or tab to be part of the label as well? I don't think it would consider the tab or space to be part of the label because this is C, but again, why would you need to know? Because you're never going to use your gotos in C, right? If you want to play around with gotos, I'm not going to be held responsible for the consequences. So, there are 3 types of loops: while, do while, and for. For loops do not work in any respect like they do in Python. So, while loops work in C the same way as they work in Python. There's basically no differences except for the curly braces, right? Do-while loops are a slight variation. So with a do-while loop, you do the stuff first, and then you test the condition at the end, right? While loops test their conditions before each loop iteration. Do-whiles test it after each loop iteration. This means that a do-while loop must execute at least one loop iteration. Aside from that, there's no semantic difference. Okay, now I'm going to tell all the TAs to grep all of the assignments, and anybody who uses a goto on any question gets a 0 on that question. That's a new rule. So, in Python, a for loop is used to iterate over the elements of a data structure, lists, dictionaries, etc. In C, for loops are pure and simple syntactic sugar for the most common loop structure. So, a for loop in C. You have an initializing statement, a condition, and an update statement, right? So, for example, we print t minus, and then we have a series of print statements printing the integer I. That's set up and controlled exclusively from the for loop, right? So we have int I is equal to 10. That's our initializer. I is greater than or equal to 0. That's our condition. Operates the same way as any loop condition. And then I minus minus, right? So that's the update. So the the sort of expanded while loop version of that would be int I equals 10 while I is the greater than or equal to 0 ... I minus minus, right? So it basically just takes all of this, compacts it onto one line. So this business where for loops iterate over arrays, or, data structures of any kind, that is a Pythonism, and I want you to completely put out of your mind that that's how things work, because you will not be pleased if you try it, because it will fail, basically. And I have one more slide, but I guess we'll cover it. Tomorrow. I think we got class tomorrow. Anyway, any questions before I end and get out of here? I think the comic at the last slide actually is still appropriate to the current discussion of go-tos. Just so you know, this is what happens every time. So, if you're going to program with go-tos, you must raptor-proof your house, or apartment, or library, or wherever it is that you're programming. And raptors will wait for you. They will hunt you. They will stalk you in the night. And just when you think the danger has passed, just when you think you're out of danger, they will come for you. Will we be online tomorrow? No, I don't believe so. I think I'll be sufficiently over it to be back on campus for tomorrow. So, yes. Well, that's actually an interesting point that you bring up. Instead of break, I'm going to go to end program break. It's kind of interesting, right? Because that's fundamentally what a break statement actually is, or a return statement even. Like, a return statement is really just a go-to end of function passing X information, right? A break statement is go-to end of loop, right? These are really just particular types of named go-tos. Once you understand what a go-to is, you can sort of see them in their various disguises all over the place. But again, generalized go-tos will produce hell on earth. So don't use them, please. Any other questions? For loops work the same in Java. Yes. Yeah, if you know some Java, that will be helpful for you. Java is basically C with classes and other things, and the JVM. It's not just C with classes, but Java is in terms of C syntax, Java is pretty damn close to C in a lot of respects. I'm pretty sure pretty much every single operator carries over from C into Java. Yeah. I'm actually teaching a course right now that uses Java, and I've never really used Java, so I'm having the opportunity to do some Java and learn that when you're a guy with a PhD in software engineering and in your 30s, you can actually flip to a computer language that's, you've never actually programmed in before pretty quickly. So that's nice. I don't imagine those students will have as good a time, but, we'll see. Once you know C, you basically know all C-based languages. It's just a matter of memorizing their little eccentricities. Okie dokie. Well, I guess that'll be it for me today. Thank you very much for your time and attention, folks. I'll see you guys tomorrow. Ciao.